Okay, Les, so let's take a look at section 6.5. So conditions for rhombuses, rectangles, and squares. So this is really similar to what we've been doing. So we're first initially given theorems about triangles or quadrilaterals, and we establish those theorems. And then the next section typically involves now showing that a quadrilateral or a given shape is what it is. And the way we do that is by showing that the theorems hold. And since they only hold for a particular shape, then we can only imply or infer that this is the shape that we have. So I'll do a few examples or run through a few theorems so you can take a look. And let's turn to page 383, theorem 616. So if the diagonals of a parallelogram are perpendicular, then the parallelogram is a rhombus. Right? So we know that this is true for rhombuses. Right? We learned that in the last section. We know that the diagonals are perpendicular in a rhombus. So this is saying is if you have a quadrilateral and you have perpendicular diagonals, then you can infer that it is a rhombus, which is a parallelogram with four congruent sides. So we have the following shape. And I kind of mentioned it a little bit earlier, but if you're asked to show that something is a rhombus, this is a good way to do it. If you can show that the diagonals are perpendicular, then that's enough to show that you have a rhombus for a parallelogram. So it's a parallelogram, so we know that the opposite sides are parallel, right? I'll just show it with an arrow. Then we have a rhombus. So a good way to show that your parallelogram is a rhombus is try and show that the diagonals are perpendicular. So this is 616. And for 617, if one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram is a rhombus. So it doesn't say both pairs, it just says one, right? So if one diagonal bisects, so we have this. This. So if that diagonal bisects, so this, and this, then we have a rhombus. Now finally, at least for these theorems here, theorem 618, if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. So this is the theorem we're going to use to show that our parallelogram is a rectangle. So we need congruent diagonals. And here we'll have to label it, otherwise it gets a little tricky. So CB congruent to AD, we have a rectangle. So again, these theorems are going to be used to show that we have either a rhombus or a rectangle. So for an example, let's try number 17. They give you a rectangle. You have your diagonals. So you're asked for what value of x in the figure, value of x is the figure the given special parallelogram is what I meant to say. So they give you this angle here, which is 3x, and then this angle here, which is 5x plus 2. Now, in order for this to be considered a rectangle, remember this angle here has to be 90 degrees. Same thing with this one, and then this one. So 5x plus 2 plus 3x needs to be 90 degrees. So if we combine like terms, so 5x and 3x gives you a total of 8x, right? we're going to go ahead and subtract 2 from both sides, right? And we get x is 11. So not too bad. Not too many challenging ones here. We just learned a couple of new theorems regarding rhombuses and rectangles. But the majority of your homework is going to be a couple of proofs. Some of them is proving some of the theorems, which can get a little bit involved. And we've done a few of those already in some of the previous sections. So I didn't give you too many for homework. But I'll have you take a look at those. I don't want to do one here because that'll make this lesson a lot longer than it needs to be, and there's not too many proofs in your homework to begin with, so we'll leave that for a later time. So let's go ahead to the next section, trapezoids and kites. Now, kites, you may not be familiar with. Trapezoids, I'm sure you've seen. So a trapezoid is quadrilateral, but with just one pair of parallel sides. So for example here. The other pair is not parallel. Sometimes this is referred to as your base, depending on how you orient this thing. This is also a base, because you can flip it upside down and be the same deal. And these are called your legs. Leg, leg. These are our base angles here. And there you go. Now we can have what's called an isosceles trapezoid. That's when the two legs are congruent. So let's get into our first theorem. We're not going to define kites quite yet. We'll get into that in a second. So the first theorem is, if a quadrilateral is an isosceles trapezoid, then each pair of base angles is congruent. So we have two pairs of base angles, right? So if this, then this. And it's for the same shape, right? That equals this, and this equals that. So for theorem, and this is 619, theorem 620 states the following: if a quadrilateral is an isosceles trapezoid, then its diagonals are congruent. And this one's not as obvious. The base angle sort of makes sense because we sort of learned that when we did triangles. So if we draw this guy, so it's first we know that it's an isosceles trapezoid, so that's the case. So the second part is that this is the case. The diagonals are congruent to each other. And obviously this still holds as well. Now before we look at the next theorem, we have to identify what it means to be the midsegment of a trapezoid. And it's not terribly difficult to see what we mean by that. So we first build our trapezoid. So if you look at the two legs, remember these are our bases. This is base 1, and this is base 2. This is leg 1, and this is leg 2. If you take the midsegments of each one of the legs, and by midsegments, remember we know what that means. That means this, this, and this is this. Those are midsegments. And if you connect the two, we're going to get our next theorem. But that's what we mean by midsegments. So the midsegment of a trapezoid is this guy here. So that's just the definition of what the midsegment is. And we're going to actually get a theorem based on this here. So first we need to know what it means to be a midsegment of a trapezoid. So now let's get into the next theorem. We'll do an example using this as well in a sec here. So if a quadrilateral is a trapezoid, then 1, the midsegment is parallel to the bases. And that one's kind of easy to see. So if we draw a midsegment, and we know that, the way I've drawn it here at least, that the bases are parallel, because that's the definition of a trapezoid. So this, when we draw a midsegment, the first thing it's saying is that the midsegment also has to be parallel to the other bases. 2, the length of the midsegment is half the sum of the lengths of the bases. So how do we write that? Well, we're going to go ahead and use the same notation that we have here in your textbook. M, N, and then T and F. So your bases are the following segments, RA and TF. Your midsegment, which we'll call MS, is MN. So the midsegment is MN, the bases are RA and TF. So the second part of that theorem, or the trapezoid midsegment theorem, is that the length of the midsegment, so MN, Kayla, is half the sum of the lengths of the bases. So the lengths of the bases are RA and TF. So half the sum, it means add them up and take half of it, and then you'll get the length of your midsegment. So this theorem is actually really useful. We use it quite a bit. So I'll do one of the examples in your homework. We're going to do number 15. Now the way you can identify that it's a midsegment is that they'll usually write this out for you, like that. Now we know that not only is it the midsegment, but they're also parallel. They give you a length here of 2x plus 1. This is x minus 1, and this is 15. Now they're asking you to figure out what EF is, and this is EF. So this actually isn't too bad. I can use the theorem that we just learned about the midsegment of trapezoids, that's theorem 6.21, and I know that if I take the sum of the bases and split it in half, I'll get the length of the midsegment, which is what they're trying to get us to figure out. They want us to know what EF is. Right? So let's take half the sum of the bases, and that should be equal to the midsegment. And that's how we get our equation. So we'll have to get rid of this fraction. There's a couple of ways to do it. I can just multiply both sides by 2. And the 1/2 goes away on the left, so I'm just left with 15 plus x minus 1. But then you have to double everything on the right-hand side. We can combine the 15 and the 1 to get 14 plus x, and that's equal to 4x plus 2. 14 plus x is equal to 4x plus 2 is what we have. Check back to see if I remember that correctly. Yeah. So we can combine like terms. I'll subtract x from either side. So this will give me 14 is equal to 3x plus 2. Then I can subtract 2 from either side. Then we can divide by 3. So not too bad, just a few steps here. We get 4. So we get x is equal to 4. The thing is, though, EF was given to you in terms of x. And they want to know what EF is. EF is 2x plus 1. So that means EF is 2 times x plus 1. X was 4, so it's a total of 9. So not too bad. Do a few of those for homework. Not too many proofs on the homework for this one. It's just sort of using that midsegment theorem for trapezoids. It's actually really useful. So we'll see it again later on in the chapter, I believe. So let's take a look at a kite. So a kite is just what you would think. It looks as the shape of a kite, like a kite that you would fly up in the air on a windy day. So a kite is a quadrilateral with 2 pairs of consecutive sides congruent and no opposite sides congruent. So 2 pairs of consecutive sides, right? It's a quadrilateral, so we need to make it such that it looks like that. So 2 pairs of consecutive sides, these are right next to each other, and so are these. this is a kite. So it's not a parallelogram, obviously, right? You can't see any sides there being parallel. It's not a rectangle for obvious reasons. The angles are all off, and the opposite sides are not congruent. The consecutive sides are congruent. It's not a rhombus, right? Because it's not a parallelogram. So this is its own shape. It's a kite. Still a quadrilateral, which is what we've been talking about this whole time. For the first theorem, theorem 622, if a quadrilateral is a kite, then its diagonals are perpendicular. So that's kind of nice to know. So if we have a kite, so they'd have to tell you it's a kite to begin with. Remember, we draw diagonals by going from one angle or one vertex to the opposite vertex. So one diagonal there, and then one diagonal here. So if we have a kite, they must be perpendicular. I'm not going to label all these because I think it's pretty straightforward. This isn't a terribly difficult theorem to visualize or understand. But this is 622. So only one theorem with kites for now. We know that diagonals are going to be perpendicular. We know that consecutive sides are congruent. So all that stuff we can use to try and determine some of the answers to these questions that we have for homework. And we'll do one with a kite. Let's do number 24 in the homework. So we draw the figure. It's a kite that looks like this. This is 90 degrees. It's a kite, so we know that this is the case. And these are our numbered angles that they're hoping to have us figure out. So for this one, it's a little tricky because knowing that diagonals are perpendicular doesn't really help out all that much. But one of the things that you can do is look at the following. If I do a diagonal there, and I label this A, B, C, and D, you'll notice that this diagonal is congruent to itself. So that means that triangle ADC is congruent to triangle ABC. So why is that important? That's important because what you are able to sort of get from that is the fact that these two angles are corresponding angles in congruent triangles. So that means that they're the same. So angle 1 is actually congruent to angle 2. So the reason that's important to know is that you have basically all the parts that you need here. You have this angle, which is 90 degrees, and now we're talking about in terms of the kite. You know that 1 and 2 are the same, and you have this angle here, which is 45. Now the sum of the interior angles for a quadrilateral is 360 degrees. So if I take the 90 degrees, which is angle A, plus angle 1 plus angle 2, which they're basically the same, I can call angle 1 and angle 2, let's call it x so we can make an equation. So I have two of those. So I have angle A, which is 90, plus angle 1 and 2, which is what we're going to call x, plus the last angle, which is 45. If we can combine our like terms, remember this is all equal to 360, right, to get 2x plus 135 equal to 360. We can subtract 135 from both sides, right? How much is that? That's a total of 60, 135, 225. And then solve for x. We can round to the nearest degree, so we can either round up or down. Well, actually, not quite. You have to keep it that because it's 360 degrees. So not too bad. I mean, you had to use a little bit of your knowledge of triangles, but again, you know, everything builds on one another here, so we have to continue to do that. So combining your like terms, making these equations, and then determining exactly what the value of x is. So now that we know the value of x, we know that angle 1 and angle 2, which is equal to x, is equal to this much. Perfect.